All right, so get this. Today, we're diving deep, way deep, into a world that blends ancient alchemy with, wait for it, starlight, and even particle physics.
Whoa, that's quite a mix. Alchemy, you mean like trying to turn lead into gold, that old chestnut?
Exactly. But here's the kicker. What was once considered pure fantasy, well, it turns out to be rooted in some pretty solid science. We've got some sources that explore how those alchemists, they were actually onto something, even without beakers and test tubes.
Huh, color me intrigued.
So let's rewind a bit. Alchemy, stars, particle accelerators, they all sound pretty different, right?
Yeah, at first glance.
But they all revolve around one big idea, the transformation of matter. Like literally changing one element into another.
Okay, I'm starting to see the connection. Like the alchemists were obsessed with turning lead into gold.
Right. And they didn't have the tools or the scientific understanding, but get this, the same concept of transformation is happening on a massive scale inside stars.
Hold on, so you're saying stars are like giant cosmic alchemists?
You got it. Stars actually forge heavier elements from lighter ones through a process called nuclear fusion.
Okay, so like that gold necklace you might be wearing, that gold was literally created inside a star.
Mind-blowing, right? We are all stardust.
Talk about alchemy on a grand scale, but how does that even happen? How does a star make gold?
Well, it all starts with hydrogen, most basic, the most abundant element in the universe. Deep inside a star's core, where the temperature and pressure are just unimaginable, hydrogen atoms are forced to fuse together.
Okay, so like a super duper intense pressure cooker for atoms.
Exactly. And when those hydrogen atoms fuse, they form helium, and in the process, release an incredible amount of energy. And guess what? That's what makes stars shine.
Oh wow, so starlight is basically a byproduct of stellar alchemy.
Precisely. And the process doesn't stop there. As a star evolves, it can fuse helium into even heavier elements like carbon, oxygen, and eventually elements like iron, and yes, even gold.
Wow, it's like a cosmic assembly line creating the very elements that make up our world.
It's mind-blowing. So we've got stars acting like giant alchemical furnaces, turning out elements through nuclear fusion. But hold on, we also mentioned particle physics. How does that fit in?
Ah, particle physics. Well, that's where we get to play a bit of cosmic catch-up here on Earth.
Oh, do tell?
Particle accelerators, those are the tools that allow us to, in a way, recreate those intense conditions found inside stars, but right here in a lab.
Wait, so it's like having a mini star on Earth. We can actually see these stellar processes happening.
You got it. By smashing atoms together at incredible speeds, we can simulate those processes in stellar cores. We're talking about nuclear reactions, the creation of new elements. It's like having a front row seat to the stellar show.
This is getting really interesting.
And guess what? Using particle accelerators, scientists have actually achieved what alchemists could only dream.
No way. They actually turned lead into gold.
Yep. By bombarding lead with neutrons in an accelerator, they managed to, in essence, transform it into gold.
So the alchemists weren't so crazy after all. But if we can make gold, why are we all swimming in it?
Well, hold your horses. The amount of gold produced is absolutely tiny. We're talking just a few atoms, and the process itself is super complex and expensive. The energy required to do it far outweighs the value of the gold produced. So, sadly, not a get-rich-quick scheme.
Oh, shucks. But even if it's not practical, the fact that we can actually mimic these stellar processes, even on a tiny scale, is pretty darn amazing. So we've got alchemy, starlight, and particle physics all intertwined.
And it's more than just mimicking. By studying these processes, we're gaining a much deeper understanding of those fundamental forces that govern the universe. Think about it. We're talking about the very origins of the elements that make up everything we see, everything we are.
Wow. So next time I look at a gold ring, I'll be thinking, hey, you started out in a star, and someone recreated your birth in a lab.
That's the spirit. We are all, in a very real sense, children of the stars. It's a wild ride, isn't it? From those early alchemists with their, well, let's be honest, pretty basic tools, to these incredible machines that are basically recreating the universe. Amazing how far we've come.
Absolutely mind-boggling. But, okay, full disclosure, when you say particle accelerator, I kind of still picture, like, something out of a sci-fi movie, and a giant lasers and all that. Can you, like, bring it down to earth a bit? What do these things actually look like? How do they work?
Okay, so picture a racetrack, right? But instead of cars, we're racing subatomic particles like protons and electrons, and they're zipping around at insane speeds, almost the speed of light.
Whoa, so they're like flying around this racetrack at warp speed. What happens then? How do they, actually collide?
So that's where things get really clever. We have these things called beamlines, basically tunnels that guide the particles along the racetrack. And at very specific points, these particles are steered into head-on collisions. Boom.
So it's like a carefully choreographed subatomic demolition derby.
You got it. And when those particles collide, the energy released is transformed into a whole bunch of new particles, like a cosmic fireworks show, all sorts of exotic particles flying out.
Wow, so from these collisions, scientists can learn more about those fundamental building blocks of matter.
Exactly. Think of it like a puzzle, but instead of cardboard pieces, we're working with subatomic particles. We look at these particles' energy, their momentum, how they interact. That's how we get clues about those fundamental forces that run the whole universe.
That sounds super complex. How do they even detect these particles? Some of them only exist for like a fraction of a second.
Ah, that's where the detectors come in. Super sophisticated instruments surrounding the collision point like layers of a high-tech onion, each layer designed to detect specific types of particles, measure their energy, their path, all that good stuff.
So it's like a super sensitive camera catching these fleeting moments of like subatomic creation and destruction.
Great analogy. And let me tell you, the data generated is just massive. We're talking about petabytes of information. Needs some serious computer power to crunch all that.
Wow. Okay, but all this talk about smashing atoms, creating new particles, kind of makes you wonder about like the safety of it all, you know? Any risks involved?
Totally valid question. Safety is the absolute priority in this type of research. These experiments happen in super controlled environments, layers upon layers of safety protocols. Plus, the amount of matter involved in the collisions is super tiny, so the energy released is, relatively speaking, small and contained.
So no chance of like accidentally creating a black hole and swallowing the Earth? Had to ask.
Haha, nope, no worries there. The energies involved in these experiments are way, way too low to do anything like that. It's a question we get a lot, though.
Good to know. But even if they're safe, I can imagine these experiments are still like incredibly complex and expensive. Probably need a lot of collaboration, right? Like scientists from around the world.
Absolutely. This is a global endeavor, no doubt about it. Scientists from all over working together at places like CERN, that's the European Organization for Nuclear Research. They run the Large Hadron Collider, the biggest, baddest particle accelerator on the planet.
So it's like a testament to, human collaboration and our shared drive to understand the universe.
Exactly. Shows that even in a world where things can feel pretty divided, the quest for knowledge can bring people together.
I love that. Okay, so we've talked about the how, the particle accelerators, the detectors, all the data analysis. But what about the why? Why is this research so important? What are those big goals of particle physics?
Well, the ultimate goal, the big dream, is to understand the fundamental nature of reality itself. What are we made of at the most basic level? What forces govern those building blocks? How did it all begin? How will it all end? Big questions.
Whoa, so it's not just about understanding tiny particles. It's about understanding, like, existence itself. No pressure particle physicists?
Pretty much. And in our quest to answer these big questions, particle physics has led to some pretty incredible technological advancements, stuff that benefits us all.
Oh, I bet. Like what?
Well, for example, the World Wide Web, yeah, the internet itself, got its start at CERN. Scientists needed a way to share data more efficiently. Boom, World Wide Web. And medical imaging, things like PET scans, rely on technologies developed for particle physics research.
So these, like, abstract, super complex ideas are actually improving our lives very real ways.
Absolutely. And as we dig deeper into these fundamental laws of nature, who knows what doors will open? New possibilities for innovation, new technologies we haven't even dreamed of.
Okay, before we get too far ahead of ourselves, let's take a step back. We've been talking about these mind-blowing connections between alchemy, starlight, particle physics, all that. Easy to get lost in the immensity of it all, but at the core, this is a human story, isn't it? It's about our curiosity, our drive to understand the universe and where we fit in.
Couldn't have said it better myself. It's a story that spans centuries, from those alchemists in their labs to today's scientists working together on these massive projects. And the story's still being written. Who knows what incredible discoveries are just around the corner.
You're right, it's exciting to think about. Speaking of discoveries, I'm really curious to hear about some of those breakthroughs in particle physics, but I think we've covered a lot of ground in this part of our deep dive. Time to give our listeners a chance to digest it all. We'll be back soon to explore those exciting discoveries and what they could mean for the future. Stay tuned. Okay, so we're back, ready to wrap up our deep dive into the amazing world of particle physics. We've talked about the history, the tech, the big picture goals, but now I got to know, what about those like aha moments, those big discoveries that have totally reshaped our understanding of the universe?
Well, one of the biggest in recent times, definitely the detection of the Higgs boson back in 2012 at the Large Hadron Collider. This was a particle that had been predicted like decades earlier, but it took years of experiments and analysis to finally definitively say, yep, it's real.
Ah, the Higgs boson. I remember when that was all over the news, they called it the God particle, right? Always sounded kind of mysterious to me. What's so special about it?
Think of it this way. It's often said that it's the particle that gives other particles mass. It's a bit of a simplification, but it kind of captures the essence. Imagine this field, okay? It's everywhere, permeates all of space. That's the Higgs field. And as particles interact with this field, they experience resistance. And that resistance, that's what we perceive as mass. The Higgs boson is the particle associated with this field.
So without the Higgs boson, everything would be like massless, just zipping around at the speed of light, no weight.
Pretty much. And if that were the case, atoms couldn't form, stars couldn't ignite, and the universe as we know it wouldn't exist.
Okay, wow, that really puts things in perspective. So finding the Higgs boson was a huge deal, right? It confirmed a lot of what scientists thought about how the universe works at that super fundamental level.
It was a huge confirmation of the standard model of particle physics, which is our best theory so far about those fundamental forces and particles that make up everything.
Best theory so far, you say? So does that mean there's still stuff out there that the standard model can't explain?
You're picking up on that, huh? Yeah, even though the standard model is incredibly successful, it doesn't explain everything. There are still some big mysteries out there, things that keep particle physicists, well, scratching their heads. For example, it can't explain dark matter or dark energy.
Dark energy. Okay, now that sounds like we're getting into like sci-fi territory.
It might sound like it, but their effects are definitely real. We can see them through their gravitational influence on the stuff we can see, regular matter. Dark matter, for example, it acts like an invisible scaffold, holding galaxies and galaxy clusters together.
So it's like some kind of cosmic glue preventing the universe from just flying apart.
Good way to put it. And then there's dark energy, which is even more mysterious. That's the thing that seems to be causing the expansion of the universe to actually speed up.
Wait, so the universe is expanding? I thought it was like a static thing. Always just been there.
That's what people thought for a long time, but observations back in the late 1990s showed that no, the universe isn't static. It's actually getting bigger, and the expansion is getting faster.
So something's pushing it apart. What could possibly have that much power?
That's the big question. We call it dark energy, but we don't really know what it is, just that it's there and having a major impact on how the universe evolves.
Okay, so we've got dark matter holding things together, dark energy pushing them apart. It's like a cosmic tug of war. And while we're talking about pushing boundaries, are there other big questions that particle physicists are trying to figure out?
One of the most exciting areas is the search for new particles, thinking that might give us clues about these mysteries. Some theories suggest that dark matter might be made of these things called Whipple interacting massive particles. Basically, they don't interact with light, but they do have mass, so they'd have gravitational effects.
So they're looking for these invisible particles that might make up the, the missing mass of the universe. That sounds like searching for a needle in a cosmic haystack.
You got it. And to help with that search, they're always developing new types of particle accelerators, ones that are even more powerful, more precise, so we can really get a close look at what's going on at those tiny levels.
It's like we're building bigger and better telescopes, but instead of looking out at the stars, we're looking inward, into the heart of matter itself. It's just incredible to think about how far we've come, but also that there's still so much we don't know.
And that's what's so cool about science. It's this never-ending journey. The more we learn, the more we realize how much more there is to discover.
I love that perspective. Okay, so we've been focusing on those big, mind-blowing questions, but all this research has real benefits here on Earth, too, right?
Oh, absolutely. Particle physics has had a hand in so many technological advancements, things in medicine, industry, even everyday life. For example, they use particle beams to sterilize medical equipment, even food. Kills bacteria without using heat or chemicals.
So it's a safe and efficient way to keep things clean. That's pretty high tech.
It is, and they use particle accelerators in materials science, too, to study the structure and properties of materials at the atomic level, which can lead to all sorts of innovations.
Like lighter airplanes, longer-lasting smartphones, maybe even materials that can repair themselves.
You're catching on, and that's just the beginning. Particle physics research is fueling innovation in so many areas.
It's really amazing to think about how studying these tiny, invisible particles can have such a huge impact on our understanding of the universe and, on our lives here on Earth.
It's a testament to human curiosity, that drive to explore the unknown, to figure things out, and it's a story that's still unfolding. Who knows what's next?
That's so true. Well, this has been an incredible journey from those early alchemists with their dreams of transforming matter to the incredible discoveries of modern physics. Thanks for joining us on this deep dive into the amazing world of particle physics. We'll catch you next time for another adventure into the realms of science and history.